Hello everyone, my name is William Blair, and today I'll be discussing the automated synthesis of effect graph policies for microservice-aware system call specialization. This work was done during an internship with my talented supervisors at the IBM Thomas J. Watson Research Center. Now, it wasn't all that long ago when a young science fiction writer named Michael Crichton introduced the public to the concept of a computer virus as a small piece of software that replicated itself across a series of androids, causing them to become malicious and systematically hunt down the guests of a theme park. Now, no one's actually attempted to build such a theme park, but if they did, we have some pretty solid solutions for securing the end hosts that would power every part of its infrastructure. In this talk, I'll be presenting a new approach for securing the microservices that make up the large cloud applications we rely on every day. Now, cloud operators face unique security challenges in running microservices on behalf of their customers, for the simple fact that running arbitrary code containing within operating system containers exposes cloud operators to enormous risk. If an adversary were to compromise, say, an end host on the computing edge, they could easily jump into a microservice container and leap out to the kernel running on a computing node, and then negatively impact the entire computing cloud. Compromised containers can wreak havoc on customers and cloud resources as a result. Operators cannot always predict what programs customers will run on their platform for the simple fact that they sell arbitrary computation to their customers. And furthermore, operators cannot rely on customers to author accurate security policies in order to contain their microservices should they become compromised. Now, one approach for securing microservices takes the form of system call specialization, which tends to consider the layered file system that makes up a microservice, containing both the entry point for the microservice, any configuration files, and application dependencies within a layered file system that comprises a container image. These frameworks pass this image through the system call specialization framework in order to produce a security policy that summarizes all of the side effects an individual microservice will occur throughout its lifetime. Now, state-of-the-art system call specialization frameworks produce these security policies and pass them to a reference monitor. And for the purposes of our presentation, let us consider these security policies as a kind of type that may be assigned to the microservice in order to restrict the system calls that it will issue throughout its lifetime. Now, these microservices run as regular user space programs and issue system calls down to the kernel. Throughout their execution, an individual microservice may become compromised and issue a malicious system call. This causes the eBPF program that's implemented within the Linux kernel that makes up the setcomp filter to then check whether or not a particular system call that issued by the compromised container conforms to the assigned security policy. Intuitively, you can think of this then as the reference monitor is checking whether or not the security policy tau models the offending system call. If the adversary has issued something outside of the security policy, this will return false, and the reference monitor setcomp will terminate the microservice in response. In this work, we consider or want to take advantage of the rich contexts that are present in container images in order to define more stateful and restricted security policies that are restricted to a particular configuration of the general purpose programs that are often found in container images. Towards this end, let us go over some of the varying levels of expressiveness that existing system call specialization frameworks contain in their security policies. Most system call specialization frameworks produce stateless policies, where you consider the policy as a bag of system calls that the microservice may issue throughout its lifetime, and if any other system calls are issued outside of this set, the reference monitor setcomp will issue a violation and terminate the microservice in response. Some policies limit access to specific resources that can then be enforced by a reference monitor, such as AppArmor. You can think of this as an extension of stateless policies that permit the microservice to issue the system calls given in the policy to a restricted set of resources contained on the system. Even more expressive policies may partition the application into distinct phases in order to enable temporal security policies. For example, an application may be split up into a boot phase where initialization occurs and a serve phase where individual requests are received and then answered by the web server. In this case, then, you have two partitions for the individual microservice, and once the microservice switches from one phase to another, it changes the valid system calls that the microservice may issue. Now, if an adversary were to come along and compromise even the more expressive policies, they may be able to achieve what's called a mimicry attack, whereby they achieve some malicious goal while issuing system calls that are allow listed by the security policy. In this setting, an adversary may, for instance, accept to a non-standard port and start disclosing sensitive information, possibly by establishing a reverse shell. These naive mimicry attacks may be common against general-purpose programs, since general-purpose programs, by definition, are implemented to fulfill various use cases. They may contain more system calls that are used for a particular configuration. As an example, consider an exec.ve system call stored within a popular web server, which is configured by a particular user simply to serve static files. This additional, very dangerous system call is not needed under this particular configuration. However, using stateless system call policies, it may be permitted since the exec.ve is given within the web server's binary. In this work, we propose microexecution as a technique for synthesizing stateful system call policies that are restricted to a particular configuration for a microservice. Now, microexecution starts by performing a static analysis to recover the control flow graph of an individual microservice entry point, which summarizes the execution paths that occur between individual basic blocks in the program. Now, static analysis may also be able to infer interprocedural edges that connect the individual control flow graphs within the application. Now, one can then infer a security policy for the whole microservice by walking the interprocedural control flow graph and collecting which of those terms issue side effects in the form of a system call, or call out to functions that may issue the syscall instruction. This may produce individual system call sequences. However, it may lead to an over-approximation of an individual microservice's behavior. The first source of an over-approximation is that the destination for indirect jumps contained within the interprocedural control flow graph may be difficult to resolve for all particular configurations of the application. Furthermore, the concrete inputs that are contained within the microservice's configuration may not be realizable or even at all obtainable by iterating a purely static representation of the program. Now, one can, on the other hand, implement a lightweight dynamic analysis by tracing individual system calls over real executions for the microservice to overcome this limitation for static analysis. However, this too has several issues present where for individual sequences of system calls, it can be difficult to determine which parts of the original program are responsible for issuing individual system calls. For example, here, it can be difficult to infer exactly which parts of the program are issuing a series of reads, or whether or not, for instance, they are being issued within an individual loop, consuming information from the server. Now, this information that can be obtained from a syscall trace, it may be difficult to then infer which individual corresponds to a part in the CFG. We propose using microexecution as a technique to combine both of these approaches in order to infer a stateful projection of the control flow graph that summarizes both sequences of system calls and concrete arguments that are passed to each individual system call. As an example here, you can consider the server first opening, reading, and then closing on an individual configuration file, and then starting up and preparing to accept requests by cloning and then dropping its user permissions. Now, this graph data structure consists of individual nodes which represent system call terms in the control flow graph, and individual nodes are annotated with concrete arguments that occur at each individual term in the CFG. Incoming edges to each node represent the syscall that occur at that term, and we use some syntactic sugar in this presentation whereby a comma present within the security policy denotes sequences of syscall nodes occurring on the same resource. This data structure, which we define formally in our paper and how we construct it during microexecution, is referred to as an effect graph. In order to synthesize effect graphs for individual microservices, we propose the micropolicy-craft architecture in order to both produce effect graphs and monitor the microservices execution for policy violations at the computing edge. Now, micropolicy-craft takes as input the layered file systems that make up the container images for a whole microservice architecture, as well as test inputs for the microservices. Test inputs often represent network inputs to the running microservice. Both of these are passed to a policy generation framework, which takes the binary file representing the microservice entry point, passes it to the binary analysis platform, which lifts the CFG and is passed to a microexecution framework, which on top of which we implemented our effect tracking plugin. This microexecution framework is able to abstract external library dependencies through an application binary interface, which we implemented and improved upon from the existing sources within Primus, and also makes use of the configuration files and library dependencies present on each layered file system container image. The result from microexecuting each entry point within Primus then yields a stateful security policy which summarizes both the system call sequences that we observe during microexecution, in addition to concrete arguments passed to each system call. We then run the container images as normal within a cloud orchestration engine, and if at runtime one becomes compromised, say by a remote adversary who begins issuing a series of malicious system calls, the sysflow telemetry system then produces a lightweight syscall trace that a microservice-aware policy monitor consumes. Now, the NPM is implemented as a plugin within the sysflow telemetry framework, and recalling our analogy of security policies to types, the NPM checks whether or not the effect graph G produced for each microservice can model the sysflow trace that's produced by each microservice. In this example, when an adversary compromises an individual microservice, the NPM will observe that G cannot model T and then raise an alert to an operator in response. Now, this framework that we've implemented poses several interesting research challenges, including correctly modeling external libraries used by each microservice, accurately recovering control flow graphs and system call arguments, scaling the analysis to real-world programs, and efficiently monitoring for policy violations at the computing edge. Now, to give you an idea of how policy synthesis works for generating each effect graph, let us consider microexecution running on a particular entry point within the Primus framework contained within BAT. Now, during microexecution, Primus will interact and obtain information contained within the layered file system in order to record the effect graph during execution. In this example here, let us imagine we're modeling an individual server that periodically reads and writes some data to disk. As microexecution occurs and the program issues system calls, we will encounter terms within the control flow graph that issue system calls. First, a read, and then at another term later on, a write system call, and then, because this is happening in a loop, we will read again from the original term. If these are the only effects that the individual server incur, we will have now a nice concise representation at these two alternatingly executed terms for the program's effects. Now, to generate the final effect graph for the server, we annotate each individual node with the concrete system call arguments that we observe during microexecution. The result then is the security policy G for the server that encodes that the server throughout its execution simply reads and writes some data to a particular database file in alternating sequence. If we then use this modeling procedure to then generate effect graphs over real-world programs, we observe that we achieve good effect coverage for our artifacts, measured by the number of effects contained within the effect graph over the total number of effectful terms present within each binary, and furthermore, microexecution can be achieved within a reasonable time frame. In addition, the policy size or number of states within the effect graph do not grow significantly even as the binaries grow in size. This allows us to maintain concise system call policies for real-world binary applications and produce effect coverage that is relevant to a particular configuration for an application, as opposed to containing all of the effects contained within the binary. Now, to see how the NPM detects policy violations for each effect graph, let us take this example subset of effect graph for the Nginx web server shown here. Now, the adversary in this case has managed to connect to an external server in order to connect to a command and control network. And the sysflow trace for this intrusion is shown here. Now, what the NPM will do is treat this effect graph as a kind of security automaton and use all of the actions that are present in the sysflow trace in order to attempt to advance the automaton and in an attempt to detect any actions that are not used within the effect graph. You can then model a policy violation using this automaton-based approach as whether or not there exists any actions that cause the automaton to become stuck, since the final connect given within the sysflow trace can no longer advance the automaton and yields a policy violation. Furthermore, in order to prevent false positive alerts, effect graphs can also support symbolic constraints. For example, allowing access to multiple host names using a regular expression, or individual folders, also via the assistance of a regular expression shown here. Now, we also showed during a performance evaluation that monitoring effect graphs can be done efficiently without inhibiting the normal operation of a particular microservice. For example, if we were to monitor an Nginx web server to act as a configuration proxy while handling 1 million requests for a backend application server running as within a microservice architecture, we observe that the Nginx's resource utilization stays manageable and the request runtime is not negatively impacted by protecting Nginx and the application server using a microservice-aware policy monitor. Essentially, embedding the security automata into the container's environment can detect policy violations without inhibiting the container's operation. Furthermore, the NPM itself utilizes few resources, and as you add more effect graphs to be monitored for a telemetry trace, it will not inhibit the operation for the whole microservice architecture, since an individual NPM can monitor multiple effect graphs concurrently, since they are just checked against the same sysflow telemetry trace. In this particular experiment, the security automata themselves only consume up to 2 cores and less than 50 megabytes of RAM on each physical computing node. Now we can put all of these pieces together in order to protect a whole microservice architecture that consists of multiple communicating microservices all running together. In this example, imagine within a hotel reservation microservice architecture, the individual search microservice becomes compromised, and an adversary attempts to go outside the intended communication links specified by the distributed effect graph defined by the composition of all of the microservice effect graphs shown here, in an attempt to disclose users' location history that's not intended by the application by reaching out directly to a MongoDB database. The NPM will observe that the effect graph does not model this particular syscall trace and then raise a violation in response. In this example here, we have shown that we have extended this stateless security policies understood by most system call specialization frameworks into a stateful data structure that can detect policy violations across whole microservice architectures for concrete individual system call arguments. In conclusion, today we've defined effect graphs as a security policy for implementing microservice-aware stateful system call specialization. We introduced micropolicy craft as a framework for synthesizing effect graph policies from microservices. We efficiently detect attacks using microservice-aware policy monitoring on top of the sysflow telemetry framework for whole microservice architectures. And finally, our tool and all of its dependencies are available as open source. Thank you.